Hi and welcome to the transmission electron microscopy lecture. A transmission electron microscope, the main idea with electron microscopy in general is that it has higher resolution than light microscope. And one can say that there's a factor of 1000 in difference between these ones. A light microscope basically has around 200 nanometer in resolution at its best. Transmission electron microscope will come down to 0.2 nanometer in resolution, or a little bit less than that also. And that means that you can have atomic resolution contrast in a modern TM. If you compare a transmission electron microscope to a standard light microscope, you know that in a light microscope you have glass lenses that do the focusing. And to adjust the focus, you change the distance between the sample and the lens, because the lens will have a fixed strength due to the curvature of the glass. In electron microscopy, you use electrons, and for that you need to have electromagnetic lenses that do the focusing. The advantage with electromagnetic lenses is that you can change the strength of the lens by adjusting the current in it. So that means that you don't need to change the distance between the sample and the lens. You can have the lens at a fixed position and then change the strength of the lenses. Basically it works exactly like your eye, you know, that can change the focusing effect by adjusting the curvature of the lens. One drawback with electromagnetic lenses is that when the electrons are focused by the lens, they will make a spiral pathway when they go through the lens. And that will make that the image that you produce on a screen below, you usually have a fluorescent screen at the bottom of the microscope, that when it hits with the electrons, it will emit light, so you can see the image with your eyes. And this image, if you change the strength of some lenses, for example you change magnification or you change the focusing level, the image will rotate. And here you can see when I demonstrate this. Here you have a microscopy image where I change the focusing lens strength. I turn this knob now, and now you can see the image rotates due to this. So when the strength increases in the lens, the image will rotate. This rotation can have a drawback when you, for example, take diffraction patterns of your sample, because you usually want to know the direction of the pattern relatively to the image view, the standard image view in a microscope. But these ones will have a rotated angle between them that will be unknown if you haven't studied it before, due to this change in lens strength that causes this rotation. So here I will draw an overview of the column in the microscope. At the top we have the filament and the gun. The filament emits the electrons, and the gun is basically an electrostatic potential that accelerates the electrons and shoots it at the sample. In the transmission electron microscope, voltages up to 200–300,000 volts is possible. Beneath the gun you have the condenser, and that is a package of electromagnetic lenses. And the purpose of this one is the same as in light microscope. To adjust so that the electron beam that's emitted from the gun will be projected onto a specific region onto the sample. That is, you want to have as much as light as possible on the region that you study. And beneath that one we have the sample. Here we put in the sample, and the one drawback with transmission electron microscopy is that the sample needs to be transparent to electrons. That usually means that the sample must be less than 200 nanometer in thickness. And 200 nanometer, that's very tough to grind down, so you usually need to take some other techniques into account. Electropolishing, ultramicrotoming, or something else. Beneath the sample you have the objective lens. It's the objective lens to do the focusing. And it's the most important one, because if you have an error in this lens, that error will be magnified by all other lenses. So it's vital that this lens is set up correctly. And beneath the objective lens comes an aperture. The purpose of this aperture, because it's located in the back focal plane of the lens, that is to cancel out the electrons that are deflected in the sample. If you do that, you can increase contrast. And I will discuss this more further later on here. Beneath this objective aperture comes actually the magnification package of lenses. That's usually 2-3 lenses that works together and magnify partly after each other. And the resulting magnification of this can be up to sort of 1 million times. And the last step of this column, that is a projector lens that projects the final resulting image onto a fluorescent screen at the bottom of the machine. And you use it as a fluorescent screen because you can't see electrons with your eyes. But when the electrons hits this fluorescent screen, the screen will emit light that you can see, and you can actually see some image then. Now I will show you a microscope image of this machine. Here we have the bright field imaging view of the transmission electron microscope. And what we see here is a sputtered aluminum sample. And that means that everything on screen here is aluminum of equal thickness. The contrast that we see, these small grains, that is aluminum crystals that's oriented different directions. As I told you, the objective aperture in the back focal plane can be used to cancel out the deflected electrons in the sample. And that's what I've done here. All the electrons that's been deflected due to this Bragg criteria has been cancelled out by the aperture. And that's why some regions have become black. And that's what makes us able to see some of the grains. We can instead choose to view a part of these deflected electrons and cancel out the central beam instead, the bright field image. So if we cancel that one out and watch the deflected part instead, we will get the dark field imaging view instead. This is sort of comparable to the light microscope, you know. So here you see the dark field imaging view. Now everything is reverse. We pick up some of the deflected electrons due to this Bragg criteria. And that makes them become white. We can view this back focal plane directly in the microscope, and here I do that. What we see now is a ring pattern. And this ring pattern is caused by this Bragg criteria. So some of the electrons will emerge due to this crystallinity of the sample at different locations outside the central part of this image. The central part, the inner dot, that is the unaffected transmitted beam that only produces this absorption contrast. If I'm now going to use this objective aperture as you see now and cancel out everything except the central beam and one of the deflected rings here as you see. And then I go back to the image view again. What we will have then is a phase contrast image. You can see it is gives some three-dimensional character to the grains. Some edges of the grains will have white regions and some edges will be black, and that makes them look like this three-dimensional. And how much these white and black regions offsets, that's depending on the strength of this defocusing of the objective lens. And as you can see, some regions becomes black because less electrons hits that part of the screen, and white becomes whiter or brighter. That's because more electrons will hit that part of the screen. And I can change the focusing strength of this contrast. And here I turn the focusing knob. And you can see these ghost white images go out and come back to these grains. Here I put in another sample for you. This is carbon black particles. And they sort of look like some macaroni shaped structures. But what I want to show you here is this phase contrast again. If I change the focusing, then we can see that the effect of this phase contrast will create a contour around each object that's either black or white, depending on which direction I turn the focusing knob. The idea in high resolution imaging is that when you do imaging lattice planes, you want to have these contours overlap periodically in relation to the lattice. And that will give you this high resolution image. And if you have a modern TM, then you can actually see atoms with these techniques. But you need to remember one thing here, and that's the bright and black regions doesn't reflect the particles. This is a phase contrast image, and it's a interference of electron beam. Depending on how you turn the focusing knob, then the atoms in this phase contrast image can either be white or black. And the only real way to know what actually going on here, and that is to model the whole system. And that can be a very hard task to do, especially if you combine several diffracted beams with this central beam, and especially if the sample itself is very complicated. If it's very clean and nice big crystal lattices, then it will become perhaps a little bit easier for you. Alright, that was lecture 1. I talked about absorption contrast and diffraction contrast as well as phase contrast. And I discussed some about how the column of the machine is built and what the electromagnetic lenses is and how it is used. And now I want you to do some of the problems that I put up below here, and see you on the next thing. Bye.